Good morning, students. I hope this video finds you well. I was looking through the assignments on OneNote that you completed yesterday. Nice job. I see that people are getting the idea and the concept very well, which is very encouraging. Don't forget we have our quiz on Friday, and this right here will be the final topic before the quiz. Linear equations in two variables. And you'll notice you'll have this in your guided notes. So let's get into it. As you want to practice, we've got some digital links for you. Further in challenge, in study guides, in practice problems, you also have some problems that can help you out as well. So let's get into it. Linear equations in two variables, which again is just another extension of what we were doing with function rules. Now, speaking of which, I want everyone to recognize that from this point forward, okay, in this unit, for all topics, they're going to be functions, guaranteed. So we don't have to use the vertical line test. Because I'm telling you that they are functions. They just happen to be functions written as linear equations, and they have two variables in them, typically an x and a y. Now, before we get into it, I want us to kind of examine the types of graphs we were looking at before and versus what we're going to be seeing right now. What do you notice between the two columns here? One of them is clearly labeled discrete, and the other one's clearly labeled continuous. And that word continuous sounds like the word continue. All the graphs that we've been doing so far, in which we're just putting on single individual points, those have all been discrete. Discrete functions. They have been functions, but they have been discrete functions. When you plot the points, especially on the ones yesterday from the assignment, did you kind of see them going in a line together? We didn't connect the points, but had we connected the points, wouldn't they all align perfectly in some sort of diagonal line? Well, today and going forward, we're going to start connecting those points. And when you start connecting the points, you're dealing with continuous functions. So before we were dealing with discrete, which is just a series of points. But when you connect those points, they're called continuous, okay? There's discrete and continuous functions. A discrete function has a graph that consists of isolated points. You guys know that word isolated? It means alone. But a continuous function has a graph that is unbroken. In other words, that line is just keep going. Here, if you connect the points, what kind of graph do you have? What kind of function do you have when you connect the points? Yeah, that's continuous. Very good. But when you don't connect the points, that's when we call it discrete. Going forward, we're going to be dealing with continuous functions. So let's start connecting those points, and let's see how, and let's see why. So here we go, folks. All right. You know, the number of solutions of an equation, or an inequality, is a very interesting detail to study. I want us to do that right now. Here's our equation. X plus 11 is equal to negative 7. I'm going to go ahead and solve this. You can as well. Solving it proved little to no difficulty. We just subtracted 11. It's just one of those one-step equations. And we know that we can always check our work, of course, by simply going back to the original untouched equation. X plus 11 is equal to negative 7. And sending in what we think the solution is, in this case, negative 18. And let's see if we get a true statement. Negative 18 plus 11 is equal to negative 7. So yeah, we got it. All right, so if we're examining the original equation, this one right up here, x plus 11 is equal to negative 7. Let me ask you something, folks. How many variables did it have? Well, it had just the one, the x. And how many solutions did it have? Just the one, negative 18. So it had one variable, x, and had one solution, negative 18. Interesting. Okay, well now let's examine an inequality. If we can solve an equation, we can solve an inequality. Heck, we had a whole unit about that. Well, here we have negative 2x minus 4 is greater than negative 3. Let's go ahead and solve that. You notice that I added 4, then I divided by negative 2. And then once I divided by negative 2, remember I had to flip the sign because I was dividing both sides by a negative. And therefore, in the end, I got x is less than negative 1/2. In other words, the solution is not negative 1/2 itself. It's any number that is less than negative 1/2. Okay, so just because it has only one variable, as we can see, x is the only variable, how many solutions did it have? Well, if I asked you to list out every single number that is less than negative 1/2, I think you might be doing that for a very, very long time. So, how many solutions is that? All numbers less than negative 1/2? It has an infinite number of solutions, right? Seriously, think about it. List every single number that's less than negative 1/2. You would literally be doing that for the rest of your life. Thus, just because it has one variable doesn't mean it has to have one solution. Many of them did, but when you get to an inequality, one variable means it has an infinite number of solutions. So I don't want you to think that one variable means only one solution. It depends on the type of equation or inequality. Well, let's go back to an equation. Look at this one now. We have x plus y is equal to 5. So it has two variables now, an x and a y. Now, how many solutions exist? How many solutions does it have? Well, I can think of one right now. What if x was 4 and y was 1? Well, that's a solution, right? What if x was 3 and y was 2? Well, that's a solution. What if x was 0 and y was 5? Well, that's a solution. So we're seeing that it has more than one solution here. You see, with two variables, we need to start to realize how many solutions it has, and not just how many solutions it has, how do we represent the solutions that it has? For example, with an inequality, we represented the solutions it had with a number line. And with an equation with one variable, we represented the number of solutions it had with just simply saying x is equal to negative 18. And this is what we need to start studying. So what we did was, with an inequality, is we drew a picture that represents the number of solutions as well. Here, with x plus 11 is equal to negative 7, we saw that x was equal to negative 18. Now if we were to represent that solution, and the solution only, x is equal to negative 18, is sort of like a graphical representation. In other words, a picture of x is equal to negative 18. We'd have a number line here, we'd have our negative 18 over here, and we'd simply put a closed out at negative 18. No need to shade one side or another, because we're not talking about numbers that are greater than negative 18, nor are we talking about numbers that are less than negative 18. We're simply talking about negative 18 itself. Boom. Full stop. But then, as you saw when we get to the inequality, of course, we did have to say, all right, let's represent all numbers less than negative 1/2 on a number line by simply shading the proper side of negative 1/2 on the number line that has all numbers that are less than negative 1/2. So the picture of the solution is the number line here. So we took this, x is less than negative 1/2, and we drew a picture of it. In other words, a graphical representation. And we took x is equal to negative 18 and drew a graphical representation of it, a picture of it. So it's another way of looking at the solution, because if there's one thing that we've been seeing, not just through this whole year, but also significantly in this unit, and especially with yesterday's homework, there's always a lot of different ways to represent the same mathematical idea. And that's what we're going for here. And look, this happens all the time in life. I mean, let's be realistic here. Which is more interesting to look at? The actual word, P-U-P-P-Y, or the picture that represents the word P-U-P-P-Y? I want to say the picture is far more interesting to look at. But we're kind of going for the same idea here, in which the picture of the equation, or the picture of the inequality, is a much more rich way of looking at the problem. It gives us a better sense of what we're dealing with here. Same with the puppy. The picture, trust me, is far more interesting for your eyes than the actual word P-U-P-P-Y, puppy. So what we'll be doing today is actually drawing pictures, in other words, a graphical representation of various equations having to do with two variables. You see, today we learn about the number of solutions and how to draw the solutions of an equation having not one, but two variables. So let's consider a two-variable equation. Here it is. 3x minus y is equal to 7. That's a linear equation, I can promise you that. And it also is a function. 3x minus y is equal to 7. You can see it has two variables, x and y. Let me ask you something, folks. Is 1, negative 4 a solution? Let's find out. Well, we know that this is x, and we know that this is y, because we know ordered pairs. So, let's see if it's a solution by sending the x and the y into the equation, and let's see if it makes the equation true. In other words, let's see if it does actually work in the equation. I'm going to get rid of this x. I'm going to replace that with 1. Remember, 3x is 3 times 1. I'm going to get rid of this y, and only this y. Notice I did not get rid of this minus sign right here. And I'm going to replace it with a negative 4. I know it's very, very easy to get rid of the minus sign when you're getting rid of a variable, but please, you're only getting rid of the variable. That is so important. I cannot stress how important that is. Only the variable gets erased. Let's see if this is a true statement. We know 3 times 1 is 3, and minus negative 4, that's saying plus 4, equals 7. And 3 plus 4, yeah, 7 does equal 7. So yes, is 1 negative 4 a solution? It absolutely is. The reason for that is it made it into the equation, and it made a true statement. So that's one solution to that equation. Are there more? Is 1 negative 4 the only solution to the equation? Oh, let's find out. Here, let's practice with 3, 4. Is 3, 4 a solution to the exact same equation? Let's find out. This is x, this is y. Let's get rid of x again, replace it with a 3. Get rid of this y, and only the y, not the minus sign, and replace it with 4. 3 times 3 is 9. 9 minus 4 is equal to 7. 9 minus 4 is 5. 5 does not equal 7. So, 3, 4. Didn't seem to work. So is that a solution? No, that's not a solution. Okay, so we've seen what is a solution and what isn't a solution. A solution to a linear equation in 2 variables needs to make the equation true. In other words, it has to make that equal sign actually do its job. In other words, what's on the left of the equal sign has to be the same thing as what's on the right. Let's try one more. Is 1229 a solution? Well, that's x, that's y. Let's get rid of x. Replace it with 12. Let's get rid of y. Replace it with 29. And let's actually do the math. 3 times 12 is 36, subtracting 9, and 36 minus 29, a little bit of mental gymnastics there, and whoa. You see that is 7. That did work. So is 1229 a solution? It sure is, and if we look back at all of our work here, we saw that to the equation 3x minus y is equal to 7, well, we found at least 2 solutions. Now, of course, we found also one that isn't a solution, but we found that this equation is 2 solutions. Does it only have 2 solutions? 1, negative 4, and 1229? How many more solutions do you think exist for the linear equation? Go ahead, shout out your answer. I heard 3, I heard 9, I heard 1,000. Higher than that, it actually has an infinite number of solutions, much like that inequality. But it's not an inequality, it's an equation. So how do we represent that? Yeah, this equation, 3x minus y, is equal to 7. You could be listing out solutions for the rest of your life, and even after you're gone, you still wouldn't even have begun the list, because that's how big infinity is. All right, so let's consider that. But let's consider and examine this a bit more by looking at a much more simpler equation, the same one we were looking at earlier. X plus y is equal to 5. Now, as we know, this equation is really asking what 2 numbers that we can replace x and y with can add together to get 5 as the sum. Here we have a lot of space to include a lot of different solutions. X is equal, y is equal. Well, we said a few earlier. We said, okay, x could be 4, y could be 1. We said x could be 3, y could be 2. We said x could be 0, y could be 5, because 3 plus 2 is equal to 5, 0 plus 5 is equal to 5, 4 plus 1 is equal to 5. But you know what? If 4 is equal to x and y is equal to 1, well, couldn't we also say that x is equal to 1, y is equal to 4? Because 4 plus 1 is 5, and 1 plus 4 is also 5. And those are 2 separate solutions. Yes, they're the same numbers, they're just in reverse order, but those are considered 2 separate solutions in this equation, x plus y is equal to 5. By that same rationale, if x is 3 and y is 2, then x could be 2 and y is 3, and x could be 5 and y is 0. So every time we get like one solution, we're effectively doubling it by simply flipping around x and y. But okay, let's be realistic here. Are those the only numbers that can add together to get 5? What if I said x was, I don't know, 1.5? Let's not throw away decimals, rational numbers in this mix here. Well, let's see here. If x is 1.5, wouldn't that make y? Go ahead and shout it out. I got 3.5. Yeah, because 1.5 plus 3.5 is equal to 5. Okay, so let's write that one twice, 3.5 and 1.5. Very good. So if we're considering decimals, okay, good. Good. All right, so let's see here. Let's say, what if I were to say 1/2? I could write a fraction, which is, of course, another form of a decimal. Well, then that would mean y is 4.5, right? 1/2 plus 4.5, which means I could say 4.5, 1/2. What about negative numbers? What if I said x is equal to, oh, I don't know, -10? Couldn't I add a number to -10 and get 5 as the result, as the sum? What would that be? Go ahead and shout it out. I think it's 15, right? -10 plus 15, that gives me positive 5. Okay, so therefore that's also 15 and -10. Can you list out at least one more? Because I'll bet every single person that is watching this video can list out one more, and every single one of those answers that each person lists out would be unique. Because keep in mind, we're not just talking about whole numbers here. We're not just talking about integers here. We're considering all real numbers. We're considering every single number that's a decimal or a fraction or negative, what have you. What two numbers, any two numbers, decimal, fraction, negative, positive, doesn't matter, can add together to get 5. How long can we be creating this list of two numbers that add together to get 5 if we're considering every number? Well, seriously, there's an infinite number of combinations, which I hope you realized earlier on, that can be created that would make the equation x plus y is equal to 5 true. I mean, we just listed out barely any of them, if you think about it. If there's an infinite number of solutions, then the ones we've listed right here, we've barely begun the list. Even though we have a bunch of them right here. Because there's an infinite number of combinations. Infinite number of two numbers that can add together to get 5. They just have to make sure that when you add them together, they get 5. Would x is 3 and y is 6 work? Why or why not? Let's find out. I'm going to get rid of x, replace it with 3. I'm going to get rid of y, replace it with 6. 3 plus 6 is equal to 5. No, that's not true. 9 doesn't equal 5. So would x is 3, y is 6 work? No, that would not work. Why? Because 6 plus 3, or 3 plus 6, does not equal 5. That's why. Okay, so we see that there are an infinite number of numbers that work, but not every combination of numbers work. They just have to equal 5 when you add them together. And I really want you to be honest with yourself here. Would simply writing out each and every possible solution be a good idea? Knowing that there's an infinite number of combinations of two numbers that can add together to get 5, would just simply listing them out, like if I said your only homework tonight, your only assignment, is to list out every single number that can add, all the two numbers that can add together to get 5. Would that be a very viable homework assignment? Would you actually want to do it? I hope not. Because that's an infinite list. You'd be doing that homework assignment for the rest of your life. So how do you quote-unquote solve an equation with an infinite number of solutions? Well, we kind of saw that when we were dealing with inequalities, didn't we? We didn't write out every single number that's less than, say, what we saw before, -1/2. No, we can't write out every number that's less than -1/2. So we represented it with a picture on the number line. Okay, a few things first before we do that with two equations. All right, let's not forget the Cartesian coordinate plane, because we're going to be using this very, very often. We know that every ordered pair right here is an x and a y coordinate. The first number is the x coordinate, which tells us to go left and right along the x-axis. And the y coordinate is the second one, which tells us to go up and down along the y coordinate. So let's see here. Let's graph -2, -9. Let's see, -2, we go left to -2, we go down to -9. Okay, good. There's -2, -9. 7, 6. Let's see here. Go to the right 7, up 6. All right, good. -3, 4. Okay, so we go left 3, we go up 4. There's -3, 4. Good. So if we remember how to do that, we're in really good shape for representing an infinite number of solutions for a two-variable equation. Now also recall something, folks. We have different types of, I want to call them lines, but not everything is a line here. Let's say you have a series of connected points that starts and ends. In other words, it does not go to infinity. Okay, and beyond. This one's called a ray. Yeah. And what happens if it does have a start, but no end? Remember, that arrow at the end does mean to infinity. Yes, and beyond. But if you have just a single point, no, that's not to infinity. That's just a start or a stop. This is called a... That's right, that's called a ray. Oh, excuse me. That first one's called a line segment. For those that noticed that, please, nice job. That first one's called a line segment. It's a section of a line. And this one, that goes to infinity. That's called a ray. But this third one, that doesn't have any ending or beginning, that's just what we call a line. Okay? That's what we call a line. So remember, there's a line segment, there's a ray, and there's just the normal traditional line. A line extends in both directions forever. Now, if we are representing all these solutions to x plus y is equal to 5, for example, and it's an infinite list of combinations, which one of these three types of lines do you think would be good? A segment, a ray, or a line? Which one doesn't have a start and doesn't have an end? Very similar to the list of all combination of numbers that add together to get 5. You're right, it's the line. So we're going to be using lines that have no start and no end to represent all solutions to a linear equation in two variables. Let me show you what I mean here. Let's put these two concepts together to draw the picture of all the solutions to x plus y is equal to 5. Here we had a few of them. We had 3, 2, we had 4, 1, we had 15, negative 10. There's another one. Couldn't we take x is equal to 3, y is equal to 2, and let's kind of transfer that over to an ordered pair, 3, 2. And x is 4, y is 1 means 4, 1. X is 15, y is negative 10 means 15, negative 10. Let's fill in the list here and here, and let's create our ordered pairs. I'll do that real quick. Now, as you can see here, I just filled in a few of the ones that we mentioned above, and I even added a new one. Negative 4 is x, y is 9, because negative 4 plus 9 does give you positive 5. So now, let's take each of these ordered pairs and let's plot them in the coordinate plane over here. So let's do that. 3, 2, let's see here. 3, 2 is right there. 4, 1 is right there. And I want you to notice kind of what's happening to these points as I plot them. Are they kind of ordering themselves in a very, very pleasing way to the eye? Let's see here, 15, negative 10. Well, 15 is going to be all the way over here, and negative 10 is going to be down there. So let's see, 9, 10, 11, 12, 13, 14, 15. I've got to extend the graph a little bit right there. That's going to be down there. 0, 5 is right up here. 2, 3 is right there. 1, 4 is right there. Negative 10, positive 15. Negative 10 is over here. I'll extend this 10, 11, 12, 13, 14, 15. So that's going to be about right, right there, between the A and the P of the picture. 3.5 and 1.5. Well, 3.5 is in between 3 and 4. 1.5 is in between... Oh, there it is. Ooh, look at that. Negative 4, positive 9 is right there. Huh. Look at all these points that we plotted, especially the ones that are actually on the coordinate plane. Do they seem to kind of organize themselves nicely? Like if I were to ask you to visualize connecting all those points, would it make a perfectly straight line? You know what I want to do? I want to put in a few more points here. And you do the same. I want you to put points on this coordinate plane that you think would be solutions to x plus y is equal to 5. Go ahead and do that and see where they fall. I went ahead and added a few more green points here. And I know these are going to be solutions. Here, let's make sure of that. Check this out. If I were to kind of like focus on, oh, I don't know, say this point right here. This is the point negative 4, excuse me, negative 3, comma 8. All right, so that means x is negative 3 and y is 8. What's negative 3 plus 8? Wow, it happens to be 5. Interesting. What about this point down here? 7, negative 2. Let's see here. What's 7 plus negative 2? That's also 5. Okay, this can't be a coincidence, can it? What about this point right here? -1, comma 6. If I add -1, 6, I get 5. All right, well, let's just do this one more right down here. Let's see here. We got 9 and -4. If I add 9 and -4, I get 5. Okay, that's interesting. Now, those new points there, they seem to also be falling in line with the other points. Nice and organized. Go ahead and put a few more points on there. Pause the video now and do it. Let's see. You see, I put in a few more purple points. This third set of points, they're all purple. And let's see if the same kind of phenomenon seems to be happening here. This is the point right here. This is 5, 0. Okay, if we add those together, we get 5. This one down here, this is 8, -3. Add those together, and yeah, we get 5. What about this purple point all the way down here? That happens to be +10, -5. Yeah, add those together. You get 5. Okay, what about this one all the way up here? This happens to be the point -5, 10. Let's see here, -5, 10. If I add -5 and 10, yeah, I get +5. Ooh, that's interesting. So every single ordered pair, if I add the two coordinates together, x and y, I get +5. And look what's happening to these points. They seem to be forming a continuous, organized manner. Okay, well, what if I were to ask you, we could do this again. And what if I asked you to pause the video again and add a few more points? And pause the video again and do it a few more times. And then pause the video again, add a few more points. And let's say I asked you to pause the video and add a few more points. And let's say I asked you to do that 1,000 more times. Wouldn't eventually you would have just a point here, 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 a point here. Okay, do it another 50 times. You'd have a point here, a point here, a point here, a point here, point here, point here, point here, point here, point here, and do it another 1,000 more times. A point here, 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 point here, point here, point here. What do you notice is happening? If I just continue for the rest of my life, literally doing nothing else during this learning off-campus time, and then even beyond that, once school is back in session, and we're all back together, and I've done nothing with my time, and I continue to do nothing with my time, but put points on every single ordered pair that happens to be an answer, a solution to x plus y is equal to 5, what do you notice is happening with all of these points? Wouldn't eventually you would have point on top of point on top of point on top of point on top of point? And if you were to look at it from afar, if you were to kind of take a step back, and you did this so many times, you did this for hours, you did this for weeks, you did this for months, and you did nothing but put point on top of point on top of point on top of point, and you were to just take a step back. Eventually, based on just the very ink in your pen or the pixelization of our stylus right here, wouldn't all of these points just kind of run together to the human eye? Because you'd have point on top of point on top of point, and what would it look like from afar? What is it starting to form right now? That's right. It's forming one long, continuous line. So what we're going to do is save ourselves the headache, as opposed to doing point after point after point. We're simply going to put on a few select points that are solutions, to our equation, and we're going to connect those with with a line, because that line represents every single solution without us having to list every single solution, because every point on the line is a solution. And how many points are actually on the line once it's created? An infinite number of points. That's really what a line is. It's a series of infinite number of connected points. Every single point on that line happens to be a solution to whatever linear equation you're dealing with here. In other words, our line, this one right here, that I'm connecting, connect the line, connect the line, connect the line. That line happens to have every solution that is going to work for x plus y is equal to 5. That's how we represent every single solution. Not by listing out every ordered pair, not by plotting every single point. That would also take forever. No, we plot a few points, and then we connect them with a line to represent all the points that we don't have to plot, because the line does the work for us. So think of it this way, folks. In other words, if you had the time, the effort, the patience, the determination to plot every single ordered pair that's a solution of x plus y is equal to 5, all the points would begin to run together to the eye, and eventually you would simply have one continuous We're talking about continuous functions. Remember that word from earlier? One continuous, that's right, line. One continuous line. There's a math joke for you. All right, so let's do this. This is how we draw the solutions to an equation having two variables. We graph the line that represents all its solutions. We don't have to write out every single solution. That would be a colossal waste of our time. We have other things to do in our lives. We have goals, we have dreams, we have things we wish to accomplish. So we're going to bypass the fact that we have to just sit there and list every single one and just simply draw the line that represents it. Any single point on this line right here is a solution to x plus y is equal to 5. This line right here. Any point that's on it is a solution. We just guaranteed that. What about points not on the line? Will they also work? Well, let's find out. Let's choose a point that's not on the line. Let's choose this one right here, this random point right here. That happens to be 5, 7. All right, so let's see, does 5, 7 work? Well, let's get rid of x, replace it with 5. Let's get rid of y, replace it with 7. So we got 12 is equal to 5. No, that didn't work, because clearly 12 is not equal to 5. Okay, well, let's try another random point. Let's try this one down. Well, let's not do it, because that's a 7 again. Let's try this one right here. Let's try -5, -8. -5, -8. Let's see here. -5 plus -8 equals 5. Well, I already know that's not going to be equal to a positive number, so it's clearly not going to be equal to 5. So that one didn't work, and that one didn't work. Let's try 0, 0, the origin. Let's see here. 0 plus 0 is equal to 5. Yeah, no, I know that's not true, so I know the origin's not going to work. What do you think? This point right here, without even calculating it, do you think it's going to work? No, it's not going to work. You know why? It's not on the line. Only points on the line are solutions. What about this point right here? No, that's not going to work. You know it's not going to work because it's not on the line. What about this point right here in the corner? Nope, not going to work. What about this point all the way out here off the grid? Nope, not going to work because it's not on the line. You see, this point right here, whatever it is, that purple one I just put on, that's going to work. That's going to work because it's on the line, right? This line, this point right here, that's all the way on the line. That's going to work because it's on the line. Only solutions on the line are just that, solutions to whatever inequality, whatever equation you're talking about. So knowing this, let's now graph more lines of equations in two variables. Let's represent every solution with a line. Using a table of values helps to keep your work organized. So here is our first equation that we're going to do together. X plus y is equal to -3. All right, we have a lot of choice here. We get to choose what points we want to plot. Now here's what I recommend, especially starting out at first right now. Let's choose a domain, the set of inputs, that's easy for us to use. Listen carefully to the words I'm about to say, folks. I always recommend, for now, your domain being -2, -1, 0, 1, 2. I repeat, -2, -1, 0, 1, 2. That way you have two easy positives to use, 1 and 2. You have two easy negatives to use, -1, -2. And of course you have 0, which is neither positive nor negative. It's the only neutral number. For your domain, for your inputs, -2, -1, 0, 1, 2. And yes, we could do this forever, but let's just plot 5 points for now. 5 points for now. Because if we have 5 points, that's enough to make our line. And if we're doing it right, they should fall in line. Just like we were seeing with x plus y is equal to 5. So this table that we have here, you'll notice that for every single box here, 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 and here, we're going to write our work and show our work inside. But I'm going to use the equation x plus y is equal to -3 each time. So I'm going to go ahead and write it in here. X plus y is equal to -3. X plus y is equal to -3. And what I'm going to do each time is I'm going to replace x and then solve for y. So my first one over here, I am simply going to get rid of x, replace it with -2. So I'm going to erase x, -2. And now I'm going to solve for y. I know that I need to add 2 to both sides. And let's see here, I get y is equal to -3 plus 2, which is a -1. So I know when x is -2, y is -1, and my first ordered pair is -2, -1. Beautiful. Hey, let's do the same for the next one. Let's get rid of -1, x, and replace it with -1. All right, so now I'm going to solve for y. Let's add 1 to both sides, and let's see here. Y is equal to -3 plus 1. That's -2, isn't it? Yeah. So when x is -1, y happens to be -2. These are linear functions, folks, so maybe you can find a pattern here. get rid of x, replace it with 0. Well, that just means y is equal to negative 3, because 0 plus y is nothing more than y. So when x is 0, y is negative 3. You noticing a pattern here? Negative 1, negative 2, negative 3 in my range. What do you think the next number is? Right over here. No, let's find out. Let's get rid of x, replace it with 1. Let's subtract 1 from both sides, and I get y is equal to negative 3 minus 1, and this is probably the number you said just a moment ago, negative 4. Make a prediction. What do you think the next number is going to be right there? I'm thinking negative 5. I hope you're thinking the same thing. Let's find out. Let's get rid of x, replace it with 2. Let's solve for y by subtracting 2 to both sides. Y is equal to negative 5. We were right, yeah. Now, of course, we could be doing these calculations literally for the rest of our lives, but I think these 5 points, 1, 2, 3, 4, I think those 5 points right there are enough to see what the line of the equation looks like. So I'm going to go ahead and plot these points. Negative 2, negative 1 is right there. And if we're doing this right, these should form a nice, beautifully organized line. 0, negative 3 is right there. 1, negative 4 is right there. 2, negative 5 is right there. And oh yeah, look at that. And we can even predict that the next point would be right here. Or the next point would be right here. But we have enough. Once you have your 5 points, go ahead and simply connect them with a perfectly straight line, and make sure that line goes across the entire coordinate plane, ladies and gentlemen. I don't want any dinky little lines right here. I want the line to bust out of the edge of the coordinate plane here and bust out of the edge, the border of the coordinate plane there. I don't want any small little lines. I want them to go across the entire coordinate plane. That's going to help you with a future topic if you get yourself used to that now. Trust me on that one. So make a nice long line. There it is. There it is. Without even having to list every single solution to x plus y is equal to negative 3, we were able to represent every single solution to x plus y is equal to negative 3. I know without a shadow of a doubt that this point right here, whatever it is, I don't care what that point is, I know it's a solution to x plus y is equal to negative 3. I know without a shadow of a doubt that this point right here, I don't care what it is, that is a solution to x plus y is equal to negative 3. I know that this point right here is a solution to x plus y is equal to negative 3. This is a solution. This is a solution. This one is. This one is. But this one's not. And this one's not. But this one is. So as you can see, every single point that's on the line is an actual solution. And we just had to simply calculate just a few points to get that solution, to get that line. We did 5. All right, let's do the next one. X is equal to 9 minus y. All right, so let's do our calculations first. Once again, I repeat, you can select any input value you want, anything in the domain, but I recommend for this time being, for the start, use negative 2, negative 1, 0, 1, and 2. 2 negatives, negative 1, negative 2, a neutral number 0, and 2 positives, 1 and 2. And we're going to use x is equal to 9 minus y. Every single calculation. Very nice. I'm going to do the first one with you, okay? And then I'm going to ask you to pause the video and try the next on your own. So let's see here. I'm going to get rid of x, replace it with negative 2, and I got to solve for y. Now careful here, that y is minus y. So I'm going to go ahead and subtract 9, because remember, I'm trying to isolate y. And so I get negative 2, negative 9, negative 2 minus 9 is negative 11. Is equal to, careful, not y, but negative y. Remember, we're getting rid of that 9, but not the minus sign behind it, just the 9. So if negative 11 is equal to negative y, ladies and gentlemen, you cannot leave your answer as negative y. Oh, no, you need a positive y. And remember, there is a phantom 1 right there, so that's negative, technically, negative 1y. So let's divide both sides by negative 1, because negative 1y is negative 1 times y, and the inverse operation of multiplying by negative 1 is to divide by negative 1. So let's see here. Negative 11 divided by negative 1 is positive 11, so positive 11 is equal to y. So when x is negative 2, y is 11. I'd like to do the next one with you as well, and then you'll do the next 3. I'm going to replace x with negative 1. I'm going to use the same set of steps here. Negative 1 minus 9 is negative 10, which is now equal to, again, not y, but rather negative y. Don't forget that negative sign comes down. And of course, that's a negative phantom 1, so I'm going to divide both sides by negative 1. And so I know that negative 10 divided by negative 1 is positive 10 is equal to y. So when I input -1, I output 10. Is there a pattern? We went from 11 to 10. Maybe you could predict the next numbers in the range. Pause the video now, and please calculate. I'll bet your prediction was true. When x is 0, y is 9. When x is 1, y was 8. When x is 2, y is 7. And again, good mathematics is good pattern recognition. If you could find the pattern nice and early, do you really have to show all of your calculations? No, I'll bet your calculations can be, quote-unquote, discovered by finding a pattern. Because like I said, folks, every single one of these functions is linear, and if it's a linear function, there's guaranteed to be a pattern to the domain and a pattern to the range. Heck, we saw that. We call that delta y, delta x, rate of dun-dun change. All right, so good. Now that we have our coordinate points, we have 5 of them. Let's put them on the graph here to the right. You go ahead and do that. Pause the video now, put them on, and then unpause it, see what you get. Well, those are my points that I simply took right from the table of values that I was just calculating from. But remember, that's a discrete function. I don't want discrete functions. We want continuous functions now. And in order to make sure that they're continuous, all you need to do is connect your points with a line. There we go. And I'm using the line tool that OneNote offers to make a perfectly straight line. And there it is. There's the line that represents every solution that x is equal to 9 minus y. Every single solution. Brilliant. Okay, we have one more to do in this guided notes. I'm going to let you guys try this one completely on your own. Pause the video, try it on your own, graph the points, connect them with a line, show me it's continuous, and then unpause, and you'll see your solutions. Let's see if they match what I got. Did you get the same thing? When I used a domain of -2, -1, 0, 1, and 2, I got the following coordinates. -2, -2, -1, 0, 0, 2, 1, 4, and 2, 6. And I showed my calculations, as you can see here, and when I plotted those points and connected them to make them a continuous function, boom, that's what my line looked like. Now, maybe you calculated properly, and I want everyone to know something. You didn't have to leave the equation just like this. I know maybe some of you were like, oh, I got to take that 2 and distribute it. You could have easily done that. You would have gotten y is equal to 2x plus 2, and if you used that equation, instead of y is equal to 2 times the quantity of x plus 1, you would have gotten the exact same numbers. You would have gotten the exact same numbers. So I don't want you to think, oh, I can't touch the equation, or should I touch the equation? Yeah, you can. You don't have to if you don't want to. As long as they're equivalent, you'll get the same results. Very, very good, guys. Very good. So as you can see, making a continuous function is just more of what we were doing previously. We're just exclusively starting with the equation, calculating a few points, in this case 5, connecting with a line and showing every single solution without having to calculate every single solution because the line represents every single solution. Nice job, everyone. Nice job. Okay, so your assignment is on Alex right now, and as you're working through it, if you need these tables and coordinate planes, blank ones, please use the ones right here below in the guided notes. Please use these tables and coordinate planes below to keep your work and calculations organized when working on your assignments. And copy and paste if you need more. I put in a bunch. But if you need more, just copy and paste the table. You guys know how copy and paste works. All right. I must say, nice job to everyone. Thank you for joining me on this incredible, continuous journey today. I hope you learned a lot from it. If you have questions, I hope you connect with me online through Google or YouTube or email. Hope you have a great day. Hope you have a good job on your assignment. And remember, because it is YouTube, be sure to like, comment, and subscribe. Click the bell for notifications. PewDiePie, I'm coming after you.